Okay, so we have spent a great deal of time talking about matrices and matrix operations and inverses and determinants, looked at applications that use those things. Now we're going to slightly change gears and look at something slightly different. And essentially the idea from a math perspective is, in math, when we see something, say fractions, you say, hey, fractions are different than integers, so I have to redefine all my operations on them. I define addition with common denominator, multiplication, multiply straight across, you all get the idea. And then you say, well, okay, now I have these rules that tell me how to add any fraction. I know if I add fractions, I get a fraction. I know if I multiply fractions, I get a fraction. I know how to find a common denominator. And from a math perspective, that's a good thing. You essentially take a whole bunch of things and find a way to classify them, because then anytime you see a fraction, you say, oh, I know all the rules that make fractions work, I'm good to go. And that's essentially what we're going to do today. Because if you think about it, maybe in terms of fractions and integers, well, fractions and integers are different. I am aware that some fractions, if the denominator is 1, they're really integers. So they're different. But at the same time, structurally speaking, they're really kind of the same. Meaning, well, I have a bunch of objects, numbers, integers, fractions. I have an operation that I call addition, and I know how to add. I have an operation that I call multiplication, and I know how to multiply. So can I maybe classify the integers and the fractions the same? Even though they're different, can I say maybe structurally speaking they work the same? And again, we're going to kind of sort of look at that, but the idea is, again, from a math perspective, if I can kind of group things together and say, hey, this thing has the same structure as this thing, has the same structure as this thing, well, then I can really work with all of them in more or less the same way. I may have to define operations different. Addition might be different with an integer than with a fraction, than with a matrix or with functions. But if they all have addition, then to a certain extent, maybe they're all kind of the same. And again, I know that may seem a little weird, but from a math perspective, that's kind of what we do. I've mentioned this for those of you who've been in some of my other classes. There's really two ways to look at things mathematically. One is to say every single thing I learn is different, and I have to learn a trick to solve this problem. Or you say, hey, pretty much everything is the exact same. And if everything is pretty much the exact same, then the tricks I already know can be applied to different types of problems. We've used that already in this class. Our understanding of vectors from physics or Calc 3 essentially applies to matrices. So from a math perspective, what is easier? To kind of say everything is more or less the same, or to say every single thing that you do is different? I think it's probably easier to assume that things are generally the same and find their similarities. So that's what we're going to do now. And what we are going to look at is what's called a vector space. And as your book points out, and I do want to make this clear, these things called vector spaces, which we're going to define here, this is the definition, meaning I do not have to prove that a vector space is a vector space. This is the definition of a vector space in the same way that we define a derivative or a function or you name it. That being said, and I think maybe I was concerned about the way your book worded it, you still have to prove that different things are vector spaces. Meaning, this is the definition, but then say, if I want to prove, we'll get to this later on, but maybe if I want to prove that the set of all continuous functions is a vector space, that I have to prove by way of this definition. But this definition we don't prove. This is simply how we define a vector space. And I will actually point out, because I know, again, a lot of you go onto Khan Academy or just YouTube in general or whatever, which is completely fine. I remember learning about vector spaces when I was a student from the book I was actually looking in. I still have the textbook, and I think there were 6 vector space properties. Your book has 10, which is not to say that the vector spaces are somehow defined different. It just means that sometimes the properties are written in a more succinct manner. So be aware of that if you look somewhere else. Don't say, wait a minute, their definition only had 9. Well, it's because they actually kind of combined 2 properties together in one for efficiency's sake. But the definition is still the same. So just be aware about that. Okay, so let V be a set on which 2 operations, which we will call vector addition and scalar multiplication, are defined. If the following hold, then V is a vector space. And like I said, there's 10 of these, so I'm not going to be able to leave them on my board as we do things because they take up most of the board. 1. U plus V is an element of V. And there's actually kind of shorthand ways of expressing all these things, which I'll get to once we write out all the definitions. Okay. 2. U plus V is equal to V plus U. 3. U plus V plus W is equal to U plus V plus W. 4. There exists a 0 such that U plus 0 is equal to U. 5. For all U in V, there exists negative U in V such that U plus negative U is equal to 0. That's the first 5. Next 5, Cu is an element of V. C times U plus V is equal to Cu plus Cv. C plus Du equals Cu plus Du. CDU equals CDU. And 10, 1 times U is equal to U. Okay, now I have to switch colors. So we have all these things, and again, just be aware, maybe right up here we'll write U and V are vectors in the set V, and C and D, I think those are the only other letters I have. Yeah, C and D are elements of R. They're just scalars. And generally speaking, when you say scalars, you're talking about the real numbers. In theory, you could define them differently. But for the purpose of everything we're doing, just assume when we talk about scalars C and D for our scalar multiplication, we mean real numbers. Okay, good. So, U plus V is an element of V, meaning if you take 2 vectors and add them together, understand again, when we say addition or scalar multiplication, our addition is entirely dependent on whatever it is we're talking about. Meaning, if the set of vectors we're talking about is the set of real numbers, then it's just regular addition. If they're rational numbers, fractions, then it's fraction addition, common denominators, blah, 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 blah. If my set V is the set of functions, that's function addition, which we know how to do. If my set of vectors V is matrices, then it's matrix addition. So addition is kind of a general term that we define, as all of you know, depending on what it is we're talking about. But essentially, if I take two objects in the set and add them together, however I define addition, I end up with an object also in the set. This is actually called closure, or we say the set V is closed. When you take things in the set and combine them, you end up with something else in the set. You never end up outside of the set. Okay, that's actually closure under addition. Right here, Cu is an element of V. If I multiply by a scalar, I get something in V. This is also closure, but this is closure under scalar multiplication. U plus V is V plus U. Addition is commutative. You have all seen commutative property before. Commutative. I can't talk and spell words at the same time. Here, U plus V plus W equals U plus V plus W. And again, I'll point out, we understand that means I add these two things together first, then add U, or I add these two things together first and then add W. It doesn't matter the order that I add them, I get the same answer. This is the associative property. Here, there exists a zero. This is not the scalar zero. This is a zero in the set V that I'm talking about. Whether that's the number zero, if my set is the real numbers, whether it's the function f of x equals 0, if I'm talking about functions, whether it's a zero vector or a zero matrix, it's a zero in whatever set I'm talking about, such that U plus 0 equals U. If I add any vector to the zero vector, I get the vector I started with. This is the identity. And it's the identity under addition. I'm kind of short on room here, so I'm just going with abbreviations here. And last, for all U in V, there exists the negative U in V such that U plus negative U equals 0. This is the inverse. And again, U plus negative U equals 0, which is the identity element from here. If I have some vector 2, 1, there's another vector negative 2, negative 1. When I combine them, I get the vector 0, 0, which is the identity vector 0. So, and again, just in terms of, say, vectors, I can always find that inverse. Okay, over here, again, we have closure under scalar multiplication. Here, C times U plus V equals CU plus CV, and C plus DU equals CU plus DU. These are both just a distributive property. Ran out of room. C times DU equals CD times U. That's the same associative property, only it's associativity under multiplication. Associative. And 1 times U equals U, which means I have an identity. And keep in mind, in this case, this is scalar multiplication. U is the vector, so that's the scalar 1. If I multiply the scalar 1, the number 1 times a vector, I get the vector I started with. And I would actually point out, all of these are properties you should have seen before. Closure, maybe you never defined it that way, but commutativity, associativity, identities, and inverses, those are all things we've seen before that you've defined when you talk about fractions and functions and things like that, which is kind of the point that I was making earlier. A lot of different sets of things have these properties, and either every time I define a new set of things, I can redefine all the properties and show that all of these things hold, or I can prove that all of those different things are vector spaces, and then once I know they're a vector space, I know all of these properties hold, and I never really have to redefine them. There's also, obviously, and we'll get to them later, a bunch of other properties that fall out of these ones right here, things you've seen before that we'll get to shortly. And if I know that I have a vector space, I never have to prove any of them. I just say, those are all properties of vector spaces. Set V is a vector space. Everything holds. So it makes it easier from a math perspective. It saves you time because once you have a vector space, you have a built-in structure to what you're talking about, and you can just assume that structure. You don't have to redefine it every time. But to get an idea here, and again, don't get confused by the wording in the book. This is the definition of a vector space, which means every vector space has these properties. If you assume something is a vector space, which occasionally we will do, then you can assume all these things hold. Generally speaking, step one is, given a set, prove that it is a vector space, and then go from there. And in order to prove something is a vector space, you have to show that all of these properties hold algebraically. The other thing, and again, I'm deliberately coming up with different examples here. When we say vector space, at least when I was a student, my assumption was then that I was talking about vectors. But we'll see, my vector space can be the set of continuous functions. My vector space can be the set of polynomials of degrees less than or equal to n for some n. My vector space can be the set of matrices. There's lots of different definitions of vector spaces. Do not assume, oh, I have to be talking about a vector, because I can be talking about a lot of different things as long as these properties hold. So I'm going to assume you have these written down, or they're in your book at the beginning of section 4.2. I have to erase them all because of room. But let's see, just to run through some examples. Example 1, R2. We know what R2 is. It's all points of the form AB. It does that form a vector space. Well, let's see. Those, again, we can think about them as vectors, the vectors in R2. Is it closed? Well, yes. In this case, and again, I do stress, your book points this out. If you are going to say that something is a vector space, you have to define the objects in that vector space in your set V, vectors in R2. You have to define what your scalars are. Again, general assumption, they're just going to be the real numbers. And you have to define addition and scalar multiplication for your given set. For most of the ones we look at, we've already defined those operations, so it's kind of given. But in general, from a structural perspective, you have to define those things and say, this is my vector space, here are the objects, here are the scalars, here is addition, here is multiplication. And so right through here, is it closed? Well, yeah, if I pick some other vector, CD, I know how I add them component-wise. I get A plus C, B plus D. Clearly, that's in R2, so I'm good there. And I'm not going to run through all of the properties. But again, is it commutative? Well, yeah, because even just looking at this to expand on my definition. That's A plus B, C plus D. What is CD plus AB? Well, that's C plus A, D plus B, but then these are real numbers, which means real number addition is commutative. I can rewrite this as A plus C, B plus D. They're equal, so it's commutative. And again, it should become clear as you work through a lot of these for homework. You've already worked through a lot of these before, because a lot of the things we've already seen, not just in this class, in other classes, are vector spaces. So a lot of times you work through these properties, distribution, associativity, commutativity, and the proofs here are the exact same. So just keep that in mind. Let's see. Associativity? Well, if I have three of them, u plus v plus w, we'll just say that's u1, u2 plus v1, v2 plus w1, w2. And then I would have to also look at u plus v plus w. But again, I don't have to take the time to do this here. Add these component-wise, then add component-wise with that. I'll get u1 plus v1 plus w1, u2 plus v2 plus w2. And then if I do it here, even if I add these first, then w, I'm going to get the exact same thing. Is there a zero vector? Well, yeah, the vector 0, 0. And then certainly, u plus 0 is going to equal u. So I have an identity, 0. It just is not the number 0, it's the vector 0, 0. What else do I need? Inverses, but sure, if u is equal to u1, u2, is there an inverse? Yeah, let negative u equal negative u1, negative u2. If I combine those together, I get 0, 0, which is my identity. And again, I know this is obvious. When you are proving something is a vector space, you have to run through all of the properties, in this case 1 through 10. I'll leave off the scalar multiplication distribution property. Again, it should be clear. Just write them out by definition. Pick vectors u, v, w if necessary. Write them out, u1, u2, v1, v2. Do the operation out, and you can prove everything pretty easily. So the vectors in R2 clearly form a vector space. Let's see, what else are these? Well, these are vectors in R2, but I could certainly replace 2 with n. And now all the vectors in Rn for any n will form a vector space. Because that 2 was just arbitrary, I could have done triples in R3 or quadruples maybe in R4. And all the operations would have worked the exact same. I would have still had an identity. I just would have added zeros to my vector based on the number of entries I needed. So all the vectors in Rn for any n will definitely give me a vector space. One, just to kind of be slightly different. And we're not going to prove this out. I want to more work through it. I don't want to write the algebra out. You can do that separately. V is equal to the set of all polynomials of degree 3 or less. So now you just have any cubic polynomial or degree less. So if you took all polynomials that are cubic, quadratic, linear, and constant, dump them all into one set, that forms a vector space. We'll think about it. If I add 2 cubic polynomials, I still get a cubic polynomial. The degree does not go up. The degree could go down if my leading terms cancel out, but the degree cannot go up. Cubic cannot become quadratic when you add 2 cubics together. And by extension, if I add a cubic to a quadratic or a quadratic to a quadratic, whatever, the degree can never go up. It can stay the same or go down. So it'll definitely be closed. Will commutativity, associativity, distribution, all that hold? Yeah, we've already proven that in other classes. Will there be an identity? Sure, the zero polynomial. Your book does point out, technically the zero polynomial has no degree, but you can also say it has degree 0, which is, for the purposes of this, how we're defining it. Degree 0 is less than degree 3. So that would certainly be in that set, and it would certainly be my identity. Does every polynomial of degree 3 or less have an inverse? Yeah, just switch all the signs around and it'll cancel out and give you 0. If I multiply by a scalar, I can change the polynomial, but I can never change its degree because I'm just multiplying by a scalar. So all the properties of scalar multiplication will hold. If I multiply by 1, I get the exact same polynomial back. So sure, those will form a vector space. One more. What about V is equal to the set of all continuous functions? And the reason I mention this is because your book does, and there's a notation we use for this. The set of all continuous real valued functions. Ran out of room. So we're only looking at real valued functions, not complex ones. The way we actually write this, we don't use V. Your book's notation is C, negative infinity to infinity, which means the set of all continuous functions defined on the real line from negative infinity to infinity. So they're real valued, not complex. And just get used to that notation now that we are going to start classifying things as vector spaces. There's kind of a lot of notation that pops up as far as shorthand ways of writing out all these vector spaces. That's why we're going through this one. But again, if you think about it, would that be closed? Well, yes, keep in mind, this is a broad range of functions here, continuous functions. Those are most trigonometric functions, tangent, cotangent, those things aren't. The reciprocal trig functions, but the regular sine, cosine definitely are. Exponential functions, logarithmic functions. Let's see. All polynomial functions. Any of those are continuous. I guess logarithmic, for the purposes of the way your book's defining it, are not defined negative infinity to infinity, so we'll throw those out. But all the other continuous functions are definitely defined negative infinity to infinity. Is that closed? Well, yeah. If I add an exponential to a sine function, the function I get out may be weird, but it'll still be continuous. If I add a polynomial to a cosine, yeah, my function may be weird, but it'll still be continuous. Is there an identity? Well, yes, the function f of x equals 0. The 0 function, that's continuous. It's a horizontal line. And 0 plus anything will give you what you started with. Does every function have an inverse, additively speaking? Yeah, just throw a negative out in front of it or switch the signs if there's more than one term. And you can cancel everything out and get 0 back. Multiplication by a scalar? Well, yeah, multiplying by a scalar isn't going to change the continuity of my function. So yeah, that will actually work. And yes, I'm working through these in English. Some of them I'm writing out, some of them I'm not. Some of them I'm deliberately having you work out for homework, because the kind of machinery of proving these things are vector spaces is one of the skills you're supposed to learn in this class. But again, once we kind of understand that we have this class of things called vector spaces, then again, the idea is, once I know that something is a vector space, then I know it has a bunch of properties. And there's a few of your book lists for properties of vector spaces. 0 times v equals 0. If CV equals 0, that implies C equals 0 or V equals 0. C0 equals 0. And negative 1V equals V. All properties we've seen before. And then keep in mind, understand here, if I multiply the scalar 0 times one of the vectors in my set, I get 0 out. Here, if I multiply any scalar times the 0 vector in my vector space, I get 0 out. Understand the difference between these two. Here, cancellation laws, zero product property, whatever you want to call it. If I multiply a scalar times a vector and get 0, one of them has to be 0, which clearly falls out of this. -1 times v, I dropped my negative, equals -v. And again, that's essentially falling out of the additive inverse property that we've kind of been using. But I now don't have to prove these for any vector space. I know they hold, so I can just assume them for any vector space that I'm working with. The last thing I want to look at, maybe as a way to understand better what a vector space is, look at one or two examples of things that are not vector spaces. And you'll be doing this for homework too, because then it maybe helps you say, wait a minute, the thing I'm looking at is missing this part or this part. The structure is slightly different, which helps you see the actual structure you're looking for. So, number one, how about z? It's a bad z. Which is the set of integers. Does that form a vector space? If I add two integers, I get an integer. 0 is an integer, so I have an identity. For any integer, 5, say, I can take -5, add them together, I get the identity. Certainly addition is commutative, associative, all that. Multiplication by a scalar is certainly distributive. Multiplication is associative, so does it form a vector space? Well, the problem is, if my scalars are the set of real numbers, what if I look at 1/2 times u? We'll just pick a number. We'll go with 5. 1/2 is equal to 5 halves. That is an element of z. That is not an element of z. So now, closure under scalar multiplication doesn't hold. My scalars, if I multiply times a vector, which in this case is an integer, I get a rational number, not an integer. So now, closure under multiplication doesn't hold. Closure under scalar multiplication. So that's not a vector space. I would point out, if you replace integers with rational numbers, then if you multiply, all the same properties will hold for rational numbers as far as addition and identity and inverse goes. Then, if you multiply a scalar times a rational number, well, would you get closure? Well, it depends on your scalar. If your scalar has to be a real number, well, then what if you multiply by like √2? Then you wouldn't be closed under scalar multiplication with rational numbers either. So again, there is an idea that we're going for here, a structure that we're looking for, and you have to think about these things. I keep checking time because this is long. Okay, we'll do one more example, similar to the one we did earlier. Polynomials of degree equal to 2. Is that a vector space? Well, actually, what if I have f of x equals x squared and g of x equals 1 plus x minus x squared? Both of those are degree 2, so they are both in my set V. But if I do f of x plus g of x, I get 1 plus x, which is a polynomial of degree 1. Which means I don't have closure under multiplication. I'm sorry, closure under addition. We're adding, not multiplying. I'm thinking about something else. Okay? Which means I'm not closed under addition. That's not a vector space. The one we looked at earlier, we had polynomials of degree 3 or less to account for things like this, where our highest term got canceled out and we lowered our degree by 1. If I require it to be of a certain degree, then I don't get closure because sometimes that highest power cancels out. And so again, we have this idea of a vector space, which is really important. We have the definition, all 10 properties. Now we want to be able to look at different sets of things, be they vectors, matrices, functions, sets of numbers, you name it, and say, is this a vector space, yes or no? You're going to be showing a lot of things are vector spaces or finding reasons why things aren't vector spaces on your homework. Because as I mentioned in the announcement that I posted, this is one of the key things you want to get out of linear algebra. This understanding of this structure that we can find and use to explain how a lot of different things work. So this is really important.